Uh, Welcome to this introductory lecture that will briefly review what is DFT. My name is Gregor Schöner, and you see a web link there that contains some more information about this whole workshop. So DFT historically is tied to the perspective on cognition that's sometimes called grounded cognition, embodied cognition, situated cognition. And it's sort of committed to these ideas there. The sentence in red here summarizes that in a very concise form. Thinking and acting are brought about by the embodied and situated brain that is shaped by evolution and development. And so this is broadly shared by many other colleagues. I mention this here because this perspective has important consequences for a neural theory of cognition, which I'll briefly summarize here. And essentially is the notion that cognitive processes share properties with sensory motor processes. So it's not actually this claim that every time you think, you're also some muscle is twitching. It's really the idea that every time you think, the processes that make that thinking possible share properties with the processes that make sensory motor processes possible. So that there's no real boundary between these two types of processes. And so some of the consequences for theory are that these processes may evolve continuously in time under many circumstances, and they may have continuous state under many circumstances, and they is a prerequisite for them to be couplable or can be coupled, that they can be coupled to sensory motor processes, the sensory motor systems. And that also entails that they may operate in closed loops through the environment, or closed loops, internal closed loops, which would be recurrent in neural jargon. And all of that implies that the states that underlie cognition must have stability properties. Anyone who knows anything about motor behavior knows that there is no possible motor behavior without stability, that is resistance to change, the ability to compensate for disturbances. And these kind of stability properties we claim, or DFT postulates, are also relevant at the cognitive level. So I have a short little excursion here into stability and dynamical systems to make this a little bit more concrete. So this is the Breitenberg metaphor of using sort of theoretical, hypothetical vehicles to illustrate how behavior emerges when a system is embedded in a structured environment. So this little thing here is supposed to be the body of an agent, of a vehicle, like an agent that can move around in the environment, called here a vehicle. Has motors here. These blocks are like wheels. Has sensors sensitive to some intensity of some physical thing, like temperature, sound, or whatever it is. And it has a nervous system that connects the sensors to the motor. So there's some inner state that is responsible, that carries that inner state. And it has a body. The body connects mechanically the sensors to the motor system. So when the motor system, the wheels move, the sensors also move. And that is what makes it a vehicle. So these are these four things: sensors, nervous system, body, and motor system. And the fifth thing is that you're in a structured environment where the sensory information that the system is sensitive to is, structured in some way. And this is the example of a Texas system where the sensory system has this negative characteristic, high intensity, low activation, and the motor system has this positive characteristic, low activation, low rotation. And that makes that the system turns towards sources of that. So if you have a little higher intensity here on the left than on the right, then that means you send a little less activation to the left motor than to the right motor. So this turns less than that, and therefore you will be sort of turning to the source, right? That's sort of a mental simulation of that happening. So if you analyze that mathematically, you find that this actually implies that there's a dynamical system there. There's, for instance, if you model the sense intensity as a function of heading, and you go through this feed-forward architecture, and then you find that in the end, as a function of your heading, the turning rate of the vehicle, which is a question of how different the turning rates of the two wheels are, is this kind of negative function of heading direction. So, this actually makes this a dynamical system. We call it behavioral dynamical system because this is a physical variable. It characterizes the orientation of the body, its driving direction, instantaneous driving direction in the world. So if you have a given heading direction, then you know how the heading direction changes. The turning rate is the rate of change of heading. And whenever the rate of change of a variable is a function of that variable, that's what we call a dynamical system. And this is a dynamical system that has attractors, one attractor here, and attractors are states that have stability properties. So if you're heading exactly in this direction, which is the direction which the source lies, where the maximum of sense intensity lies, then the turning rate is 0. So you keep going straight toward the source. And if you're heading a little bit to the right, then you have a negative turning rate. So you will, next moment in time, have a heading that is closer to the source. And similarly, if you on the left, you have a positive turning rate, so your heading will increase, and heading will be attracted to the direction of where the source lies. And that makes it an attractor. And an attractor is really just a fixed point with stability properties, asymptotic stability, converging in time to the state. So this stability of the behavior that arises here is critical to the system actually working in the real world, so that there will be, if there are physical disturbances, the wheels don't turn perfectly, or there's some pebbles and the vehicle would deviate from the correct direction, then it would return through the attractor property to the correct direction. And similarly, if the environment actually changes, or as the vehicle drives, actually the heading in which the source lies may change, then the system tracks the attractor, so follows these changes, and that gives gives the behavior this invariance under changes in the environment. So that's a very important property. A system like that, so this is like a control system, right, a feedback system, but it actually is more than that because it can do simple forms of decisions, so simple sensory motor cognition, if you wish. So for instance, if there's two sources in the environment, the intensity distribution might be bimodal. And if you go through the same logic, that leads to two possible attractors around one source, the direction to one source, and the direction to another source would be a bistable dynamics. And the system would select one of those just based on its initial heading direction, and then start turning. Let's say if it's right on the boundary between those two, it would be really make that decision. And other than that, it will be just converging to one of those two. And the attractor property of these behavioral states makes that this decision is stabilized. It doesn't change its mind all the time, and it doesn't fluctuate back and forth. So this is still the sensory motor decision because it's the state of the body that determines what you're doing. When we think about cognitive decisions, like here, for instance, select one category, like select the book over the cup, then the selection would not take place, and the state would not be stored in the physical properties, but in some kind of internal properties here, hinted at some neural network that stores the neural state that represents the decision. And our argument is that that inner state also needs to stabilize the decision, so that as the vehicle has variable sensory information, for instance, about the possible choices, it will not flip-flop between the possible choices, but will be stabilized on one of those particular choice, maybe until there's overwhelming evidence in the opposite direction. And generally, this is based on recurrent neural networks. So you need to store state, you need some recurrency. It's no longer possible to do that just by a feed-forward neural system, even though in the previous slide we saw that even a purely feed-forward nervous system like this one, if it's in an outer loop, it can actually make attractors and can make decisions. But for this to happen in the neural system, you need recurrent neural dynamics, and DFT is really about that, and I'll explain that in a little moment. So this is just like a very macroscopic flavor of what's to come. Now we think of DFT as a neural theory of cognition, or we argue that it's a neural theory of cognition, and that's the other thing the other piece of background, embodiment, groundedness, and I want to talk briefly about what it means that it's a neural theory of cognition, and that's. Even though it sounds so straightforward, it's not actually quite as clear what that really means. And one contrast I want to make with a very reductionist for instance, computational neuroscience style mechanistic account, that will be then maybe considered to be neural by many. And that goes deep, and that's something we can discuss. It goes deep to a certain kind of epistemology that is common in biology, where you think extensive description makes sense, where you really say this neuron does that, or that neurotransmitter does this, and so on. And that could be a goal, to have a complete description of everything in neural terms. But the fact that thinking and acting are not as such really reproducible, like essentially all behavioral psychological phenomena are not. They really depend on history, on context, and so on. That hints that extensive description might not really be the right level of a neural theory of cognition. So instead, what a neural theory of cognition is more a physics-like account, where we have certain laws or constraints or irregularities, different terms for the same thing. So reproducible aspects of behavior, from the old psychophysical laws to the more complex modern insights into cognitive processes, and where we would account for these laws by theory. And when multiple of these laws are linked, then that's actually what we usually call explanation. And usually in explanation, we usually think of some laws as being more fundamental than others, and then we derive from the more fundamental, the more specific laws. And so a neural account in this sense is this particular case where the laws or principles that we try to derive behavior from are neural ones, or come from the neural level. And so a neural process account, that's what we're really aiming at, would be a case where these neural laws don't just abstractly constrain or derive, the behavioral laws, but they actually cause them. That the causal would ultimately mean that if you have an understanding of these neural principles, you can actually make a system that generates the behavior. If you demonstrate it on a robot, this is just maybe a conceptual robot like the Breitenberg vehicle, then you can show that they can cause the behavior. And that's sort of the spirit in which DFT is supposed to be a neural theory of cognition. So the question is, what kind of neural laws or principles are we actually referring to? And there, I'll broadly characterize that, and that's where I'll review two aspects that are important. So on the one hand, DFT is actually a special case of connectionism. So we're certainly sharing with connectionism. I've sort of pointed out the three fundamental assumptions of connectionism, and that activation is the relevant state variable. So it's an activation state of neural networks. We'll make particular choices about that. What is particular in our choice is that we'll think of these as representing populations of neurons rather than individual neurons. That one goes to a population level also in terms of characterizing the nonlinear operation of neural networks by sigmoidal threshold functions rather than by spiking mechanisms. So that's a contrast to be made. So it's a bit more macroscopic than spiking. And that the function significance of any activation anywhere in these networks or in these fields is ultimately established by the pattern of connectivity. So it's not information in a neural network. Information is just an interpretation of activity, and that interpretation is based on the connectivity, ultimately to the sensory motor surfaces. So there we're sharing this with connectionism, but there are two critical elements that I'm going to review a little bit more detail, two additional principles that are not in contradiction with connection, but that are more specific, that most connectionist networks don't really focus on. The first principle we sometimes refer to as time, somewhat abstractly, or autonomy, but we'll make it very concrete shortly. And this is based on, or comes from the insight that most connectionist accounts are ultimately conceptually input driven. That is, many of these networks are by themselves not doing anything. They're just waiting, reacting for some input, and then they give an output, react to that output. Not all networks. Again, DFT is part of connectionism. But that's certainly conceptually the framework. In that sense, quite still tied to information processing. And we argued that action and thought are actually not primarily driven by input. They are primarily driven by the inner state of the mind or the brain. And that inner state can only arise and persist, and sustain changes in input when they have these stability properties, and that's what we call the neural attractors. And then specifically, we will be arguing that, or DFT is having a concrete proposal for how these attractors arise and disappear in instability. So an attractor, if it becomes unstable, disappears as a attractor. And it might also suddenly appear because it was previously unstable and now it's stable. And I will briefly sketch how that is actually the basis for autonomous behavior, for sequences of inner states that the system steps through in an autonomous way that's not driven primarily by input, that could be driven internally. So technically, these stabilities and instabilities come from neural dynamics. So neural dynamics is not really different from other neural networks, but neural dynamics that have recurrent connectivity that is dominant, that is very strong, and therefore has stronger than input, for instance. So we'll go more deeply into that. The second principle we sometimes abstractly refer to as space, or the logic of space. And it's the notion that these attractor states that we're postulating are embedded in low-dimensional continuous spaces, making them neural fields. I'll illustrate that in a moment. And they can be coupled. So coupling patterns are organized by these spaces. And in particular, when many of these different populations, these different fields share certain dimensions, and then new phenomena arise. And I refer to that as flexible binding. And that is really the basis in DFT for reaching higher cognition, grounded higher cognition in the sense linked or linkable to sensory and motor behavior. But also showing some of the hallmarks of productivity, compositionality, and systematicity, for instance. Now, this is something I will just give you a flavor of. This would be a much so that we can discuss. It's a much of course it would take a couple of hours to go through all the details of that. So I'll review these two ideas, and I do that by first going to space, then to time, and then coupling the two. And that should only take about 15 minutes or so. So again, space. So the notion in DFT is that activation of neural populations carries functional meaning through, as fields over dimensions. So for instance, here I'm illustrating that if you want to represent the motion of a single element of contrast in the visual array, it's characterized by where in the visual array and motion direction. These are actually 3 dimensions. The speed is actually a separate thing. I didn't address that here. And 2 of these dimensions are plotted here for simplicity, so only the horizontal position and the motion direction. And the notion is that an activation field would be spanning the space so that one particular motion is a location in this space, and the location would be represented by a peak of activation. So suprathreshold activation, 0 is supposed to be where the sigmoid is. Suprathreshold activation indicates that there's significant activation. It would be standing for a particular horizontal position, a particular motion direction. And it's actually a 3-dimensional field that I didn't plot here. So the dimensions x that span this activation field would be here, these 2 numbers. And similar, if you have a human plans a movement of a particular to an object with a particular distance, which makes the movement amplitude and movement direction, then the notion would be that these movement parameters span a space, and there's a neural field that represents that space, and again, a peak over a particular location would be represent the intention to move in that direction. Some of you might immediately recognize this as population coding for movement parameters a la Jacopoulos, right? And this you might recognize as receptive fields and tuning curves and so on. And in fact, that's how these fields arise, right? These spaces come from forward connectivity that creates what is commonly called neural maps. So for instance, if you're from the retina or some other sensory surface, you have regular forward connectivity onto a field of a certain dimensionality, then the meaning of activation patterns here, the meaning of this dimension, is defined by this forward connectivity. For instance, if it's just retinotopic, then it will be a representation of visual space. Or if it's a feature extraction, connectivity, then this could be movement direction or color or orientation or whatever it is, right? And this notion in neurophysiology of a neural map is when one looks at this dimension as being the cortical surface, while the population view is that you're actually ignoring where it's on the surface. You're just looking at what is what the tuning curve is. So what is the location in the space of stimuli in this case that is represented at these different locations, right? This could even, you don't actually need necessarily this to be a whole space. This could be nodes, discrete categories, and we'll come to that a little later. And have many different mappings like that. And you could have the reverse. That is, you could have activation patterns over some dimension, and the meaning of that dimension comes from the forward connectivity to ultimately the muscles and their reflex loops. The reflex loop and muscles are always dynamical systems, so that's why I plotted this as a dynamical system, just like the Breitenberg vehicle. And so this forward connectivity would determine what kind of attractor states arise here in the periphery. And that's how this population then, the dimension of this population acquires the meaning of having these movement parameters, right? And of course, there's a lot more to be said about that. We've actually done this concretely, this mapping out the relationship between neural connectivity and population code as approximations of fields by using population code methods, but I'm not going to go there. So that's how these spaces come about. And it will be not more complex than that throughout our theory. Now, the other aspect is time autonomy, and I talked about neural dynamics. So this is a neural dynamical system. The activation U has the rate of change is a function of U. Here plotted is actually linear function, and this is supposed to be input coming from the sensory surface, for instance, and the input sort of lifts this here up, and therefore the attractor that is at the negative resting level here without input is shifted here to the right, and you have an attractor state at this positive level of attraction. And so if you plot the time course when it's initially no input and then you apply that input, the attractor shifts, the system tracks the attractor, relaxes to the attractor, and the sigmoid threshold function then will go from 0 to some non-zero point at some point. So this is essentially an abstract simplification of the membrane dynamics of neurons. So when you replace spiking by sigmoid, you're talking about populations of neurons, and this would be like the population membrane dynamics. We're really concretely modeling the time scale on which this happens to be the time scale of membranes, which is about 10 to something 20 milliseconds, and that's a real constraint for our architectures, right? So this is the very simple neurodynamics. This is nothing new. This has been done since the 70s, and we know a lot about that in the meantime. Population level, lifting the membrane dynamics to the population level. So this is also just still input driven, right? So we get to the properties that we're interested in when we go beyond just input driven activation, and we're talking here about recurrent connectivity, and that's strong in a sense that I'll make concrete. So here mathematically formulated by adding here a contribution that depends on activation at some other locations in a neural population. So now it's a whole population that we're looking at. So we're summing or integrating over all other locations X prime when we're looking at the rate of change of an individual neuron. And depending on this, so sigma is here, I changed the letter, should be the sigmoid function here. Previously that was called G, yes, sigma, sorry. Is that is connected with a weight. This would be the connectivity pattern, the synaptic strength, and that can be positive. That will be then a positive contribution, excitatory contribution. It could be negative, would be an inhibitory contribution. And so the generic pattern that we're postulating is that this is just a function of the distance between the location we're looking at and the location whose contribution we're considering. That's the homogeneity assumption. That is only an approximation. It's never perfectly true. And that for short distances, this would be excitatory. So once you have activation, they're sort of mutually excitatory within positive, suprathreshold activation patterns. And that if you look at larger distances, there's overall inhibitory connections, so that you have long distance, a peak here would suppress any other peak at a longer distance. And that pattern of, this is a common pattern of activation in cortex, and that pattern of activation leads to peaks, localized activation patterns in, depending on the number of dimensions, being attractor states being stable. Essentially, the excitatory interaction prevents the peak from decaying, and the inhibitor interaction prevents the peak from being from competing inputs from some other being inhibited away by some other input. So that's also not new. This goes back to Wilson Cowan and Amari in the 70s and so on. And actually, the fact that this interaction is strong, which will lead to activation that does not actually depend on input always, was then interpreted primarily in terms of things like epilepsy or in terms of oscillations and even hallucinations and so on. And so we're making much more psychological use of these the activation patterns that are not driven by input. Now, the core phenomenon is how these peaks arise. So when you're looking at a localized input, then there can be two possible attractor states for that. Either there is a peak that's suprathreshold, so there is above zero. Zero is here the threshold. So the interaction contributes. Now we call this thing interaction. It's just another word for recurrent connectivity within the population. So then this is a peak that's stabilized by self-excitation, for instance. And there can be at certain input levels also a subthreshold state that's also stable. So it's really bistable, that system. And that bistability is then caused by the interaction, that there's this gap between subthreshold and suprathreshold. That's critical. That's sort of what stabilizes decisions, that the state in which this field makes a suprathreshold state, and that thus will now affect downstream systems, and will do something, whatever the architecture, the role it plays in architecture, that is a finite distance away, non-zero distance away from the state in which it doesn't. So it's not really just going through the segment. There's a real gap. So that's how decisions are stabilized. This is a detection decision. We call it a detection decision in the sense that whatever that field stands for, you're now saying there is something in that field. There is a peak that will have impact. So when this happens, you have made a decision, a detection decision. When you have the subthreshold peak, you don't have a decision like that. Now, the peak arises when the subthreshold state becomes unstable. So that's the bistable goes to monostable, so you only can have a peak. And that happens when you increase input enough. And here, this little simulation shows that. So here, the green is the field, and the blue is the input. And you see that the input rose, and that induced the peak. Now you see this sigmoided peak. The red line is the sigmoid applied to the peak is non-zero, even though the input has returned to the original value. So here you see it's actually bistable. That is, at this level, it is both possible to have the subthreshold state and the suprathreshold state. So the subthreshold state became unstable as input was pushed here to, in this case, the zero line. Blue is actually the input minus the resting state. So resting state is a negative activation level, so no sigmoid, no response of the sigmoid. So detection instability is how the peak arises. That is, even if you're initially in the subthreshold state, you're forced to be in the peak state, and then you stay in the peak state, even if your input was only transient, the input that was sufficient to induce the peak. There is also the reverse detection. That is, when the input goes lower than certainly this level, some certain level, then the bistability is destroyed, but now the activation peak becomes unstable. So here in the simulation, we lower this, the peak decays, we lower it all the way to zero here. So it's sort of like a flip-flop, right? You have a bistable regime, and you turn on by making the zero state unstable, then you switch to on. And if you want to switch it off, you have to make the one state unstable, and then you go to zero. But to maintain either decision, 0 or 1, you don't need the input. You have an instant. That's actually also what the long short-term LSTM, I forget the exact word for that, is also essentially a thing like that. It uses very similar logic. So typically, we're looking at detection, of course, at the same time as a selection. That is, there's not just one peak that could be formed, but multiple peaks. So here, for instance, you have two inputs, then one of them can generate the peak, and the other cannot. And this suppression here, that now you see the same input, the blue line, but the peak is actually really suppressed here over this one, and that's from the inhibitory interaction, right? And that's how selections are made, and quite typically, selections are made at detection. That is, when a peak is induced, then you have the possibility to even have stochasticity, for instance, or to bias the selection in subtle ways, while it is exceedingly rare for an input system to have multiple different locations of input and then randomly switch between those. That would be very, very uncommon because of the stability of the peaks. This here is, it's really driven by input, but you can actually also have cases in which the decision amounts to amplifying small differences. So here I'm suggesting the field is slightly inhomogeneous. There's a little bit more input here at 3 locations. You see a little bit of a modulated state. It's all sub-threshold. And now what in the simulation I'm doing is really just add a boost to the whole system. So the boost doesn't actually say which state should be selected. And then the system stochastically, you see some noise here on top, stochastically selects one of those. So for instance, here selects the left one here in this case. And if you do that again, this is just 2 videos I made this way, then it selects, for instance, some other state. And so this has multiple very important implications. So this is something that in DFT, as the subclass of neural networks, makes that it can translate small differences into macroscopic states. This peak here isn't really any different from a peak that is shaped or formed when there's a very strong input signal. So, for instance, it really changes the requirements on learning, on synaptic differences. You don't have to make a real difference between the different choices. You can amplify the difference between choices by the recurrent connectivity. And it also shows that it's the continuous spaces that are the achievements, and coming from the sensory motor originally. The categorical states come for free. I mean, you can very easily break the symmetry and get categories from systems like that. The harder thing is to keep them homogeneous, and this is actually a real challenge which we can discuss. Mention one more thing, that you can have conditions under which the reverse detection instability isn't in reach. So here the input induces a peak. I have actually some interaction that is spatially limited. And if that inducing input is gone, the peak can remain. It really means that the reverse detection instability would be at negative input. And that is how activation can be sustained without input. That's sort of a model of working memory, essentially. And that, sort of a very clear example of how the inner state then can drive behavior without not being input driven. And essentially, we're arguing that almost everything that you do in terms of thinking and acting is actually driven by activation of this kind. It's actually not triggered by input. In fact, most sensory inputs are transient in nature and only briefly, put you into the right attractor, and then you're actually acting on working memory. In fact, all the visual surround that you're looking at is most of the time working memory, and only occasionally you update that through by, for instance, a gaze shift and looking at something. So this is, we claim, the detection instability in particular is the source of autonomous acting and processing. This is a little bit more difficult to illustrate than I've struggled for years to find a good illustration. I have another attempt at that. The key trick for this was actually developed by Julius and Emiskeos here. And this is a little mini architecture that I'm using to illustrate this idea, and also introduce this notion of mini architecture. So DFT actually really has only certain core elements, and the core element I just reviewed is actually the detection stability together with selection. That comes from the strong recurrent connectivity. The second one that I will be reviewing in a moment is this different coupling patterns. And then from just these very, very limited key elements, you can build small architectures, so coupling multiple fields and multiple nodes and so on, that achieve certain elementary cognitive functions. There's no claim that there's a limited number of these. I mean, actually, there's limited, but that we have a complete catalog of these. So this is one of the many architectures that we use to understand sequence generation. And so it borrows jargon, the way we name these fields, borrows jargon from sort of theory of intentionality in philosophy. So we're saying that if you have some intention, let's say a motor intention or some cognitive intention, so something you want to bring about, maybe a particular value along that dimension, then you have a peak in a appropriate field. Let's say it's a movement direction or it's some kind of like committing something to memory would be a cognitive intention. I have a peak here, and that peak, that the field is connected through maybe something learned to some other field over some other dimension that is the outcome predicted when you do that intention, what will be the case when you have achieved it. And so this red line is that prediction. So in other words, this peak makes a subthreshold input to this field that at the location where the outcome of that, when that intention is realized, is represented. We call that the condition of satisfaction field, and that borrows jargon from philosophy. And then the notion is that this condition of satisfaction field would receive input from other sources. So if it's a motor intention, from ultimately some sensory states, so this would be a perceptual system, some sensory states that would push this here through the detection instability, make a peak here, or it could be through some neural connection. If it's a neural state, like you have created a working memory of something, or you have visually searched something, that then the neural state provides that confirming input. And when that input is, as predicted, overlaps this intention, is realized, the peak is generated. And this field then, maybe through some inhibitory interference, inhibits the original field, getting rid of this intention, and then ultimately leading, you're done. That's the discrete transition, and that reverse detection instability here makes that then you no longer predict this, and you can arrange that. Then the fact that this prediction falls away makes this peak go through the reverse detection instability, and then you're done. I'll illustrate this here in this little toy example. So here, this intention is along some dimension. It essentially rotates this thing. I'm not really saying exactly how that happens. So whenever there's suprathreshold activation, it rotates this thing here. And then there is some perceptual process that observes this orientation. So dimensions orientation, the perceptual system picks up the orientation. I've indicated the orientations that are here, that are represented along this field. And the intention predicts the condition of satisfaction here, and this field inhibits the intention field, and the perceptual field will just pick up what the actual intention is. So let's run that, and then I'll take that apart. So here you see this is the current input from that, and when these two overlap, you get the inhibition. So I'll run it one more time. So the intention, makes this prediction. This is sustained, and then this stops because this only moves when you have the intention to move it, right? This is like a toy example for that. So this explains essentially how discrete transitions of states happen. So what happens in here is that when the condition of satisfaction is obtained, so this overlaps enough, then detection instability happens here. That's what this is, this moment in time. That detection instability makes a discrete change, right? And that detection instability will make that this goes through reverse detection instability, the peak goes away, and then a moment later, this goes through reverse detection instability, and then then you're done. Then this field is open again, and then the next action that would occur is a question just of what else happens in the architecture, right? So this is sort of the core of how autonomy arises. I'm not sure how easy it is to immediately understand that. Okay, second and last point here about core elements of cognition is now to couple spaces and use detection instability together. So combining the instability we just looked at with coupling patterns in space, and that leads to higher cognition. I'll illustrate that through just some complex architecture without explanation, just show that it does that in principle. And the particular aspect I want to emphasize is coupling through how binding through shared dimension happens with coupling patterns. I'll start with just an individual field. This is what we would call a joint representation. That is, the different dimensions of a field don't have to be of the same nature. Like here, this is let's say along this dimension, this field is sensitive to spatial, let's say retinal information here from the visual array, and along this dimension, it's sensitive to hue of color. We always do this as a very easy to visualize, even though it's not nearly realistic. So a hue value. So that this visual array makes 2D input that is at this location, a green would induce a peak here by virtue of the forward connectivity from the sensory surface. And this location would create a peak because of the retinal position and the color. So in a joint representation, joint representation means you have neurons tuned to every combination of the values, right? And that's something very commonly we have, like in visual cortex, we have these feature fields and so on. So they're in that sense always bound, right? They're joint representations. The only thing you can do is unbind them by extracting the unbound information. So if I sum along the spatial location and project into a field that's just one dimension over color, then I could get 2 peaks at the 2 colors that occur and similarly get 2 peaks at the 2 spatial locations that occur. That would be like a seance map. And this reducing the dimensionality is called contraction coupling, right? You sum along some dimension. You can do that in multiple dimensions. For instance, you could sum along just the 3rd dimension, and there you can see multiple different ways of how to do that. The reverse is expansion mapping, and that would be the mechanism of how you could combine unbound information into a bound representation, which is what a mental map would be about. So for instance, here this field, the same kind of arrangement, but now this field does not get any direct input from the visual array, but we make a map of, saying I have a blue object and I have this location, and I want to create a representation of that, and that will be an expansion mapping. We'll put a ridge in here, a ridge in there, and I can arrange that where they overlap, a detection instability occurs that puts a peak here in this location, right? And that's how I could build a mental map. So expansion couplings, this is the ridge case. It can be also slices, and it can be cylinders and so on, depending on the dimensionality. This is actually already anticipated. This is where the binding problem arises. That is, if you want to do that for multiple objects, you have to do one at a time, because if you just give it a bimodal input along both dimensions, you don't know which corresponds to which, right? So actually, if you analyze it a little bit better, there's a coordinate frame issue hidden here, and I'll come back to that. But clearly here, one at a time is obligatory. This Q selection, or sometimes is sort of the model of bias competition. So this is combining the expansion and contraction mapping. So if you have the field driven by input, so for instance, if these 2 locations of input, you could select one of those by having a Q. Like you say, I want to know where the blue is, and you would have this one-dimensional field would have a peak for blue. That's your search Q. And then you give a ridge into that and arrange that detection instability only happens where the 2D input is boosted by the ridge, and that creates that peak. And then you can project out through a contraction mapping the location of the blue, the location of the blue, and the answers. That can be generalized a lot. Right? And that's also an important component. Now, this is all just prerequisites. In a sense, there's no new element here except for these coupling patterns. Now, the critical idea is that when you go into cognitive architectures of vision, of action and thinking, that you're not finding extremely high-dimensional fields that represent the joint representations, where every combination of every feature value with every location, there's extra neurons for that, right? That would not be plausible. It's not nearly real. And so instead, what we're postulating is that they're separate populations. So there are fields. So here, taking an example, they all have retinal space, XY, but then there's a field for color neurons and for orientation neurons and for size neurons, so on. So separate feature fields that all share a dimension. Here, the classical Treisman idea that the location shared is some kind of spatial dimension. And I'll generalize that in a moment. So when you do that, you can use these expansion contraction couplings to link these different fields. So you can, for instance, say, if I know the location I want to look at, you put a cylinder kind of coupling, an expansion coupling into all these different fields, and that find the peaks that overlap with that cylinder, and therefore extract, and then through a contraction coupling, extract the value, for instance, which size, which orientation, which color is at that location. And there's effectively binding these different feature values to each other, just in the classical treatment sense. So here's an example of how that would be really used. For instance, if you have this display on your retina and you're building a memory of that scene, this would be your memory. So the color field and the orientation field are separate. It's just 2D examples. And so what you want to build is build a working memory representation where sustained peaks arise at the correct locations in space and in color space, and the correct locations in space and in orientation space. And this map would be actually over a allocentric frame. It doesn't make sense to have scene memory in retinal space, and there's a lot of evidence that we can do that effectively in allocentric space. There's some complication how to actually do that. And then the notion would be that you're doing that by selectively attending to items here. So you have a spatial attention here on the leftmost red target, that's this peak and that peak. You, through a contraction mapping, you represent that in separate fields, which then project here. This is sort of a copy of that, which is globally selective, so only a single peak forms. So you're putting in this ridge here as an expansion mapping at this color, and similar for orientation. And the second ridge is provided by information about the spatial location, but that's now in allocentric frames. So in other words, the coordinate transform from the retinal to the allocentric. I'll say something about that in a moment. And so now you can reassemble, make a map really of this visual array, one item at a time, and then you put it into the sustained mode here. And this could be solved different ways. There's just one proposal how to do that. So here's a little video that illustrates that idea. It's the same sketch, and you see here the retinal location. You're selecting this object, and now you see the allocentric is actually really shifted over the retinal. It's not identical here, and that does the so selects one at a time. And the fact that this is organized in sequence really comes from, in the architecture, there being condition of satisfaction kind of modes that notice that you have generated a peak and that you're done, and then you're doing the next selection and so on. Now that's an example of how the binding through space really works. So the coordinate transforms in here are really the same sort of thing. So essentially, if you do a coordinate transform, you also need a joint representation. Joint representation, for instance, this is the example of a transformation from retinal to some kind of head-centered or body-centered space. And the variable that controls the relationship between the two spaces is your gaze angle. And what you need is a joint representation of gaze angle and retinal representation. So this would be a field that along one dimension has retinal and the other has gaze angle. This is actually something observed in parietal cortex called gain fields for some reason. And you don't have a direct sensor for both of these. So what you actually do is you assemble them by having retinal information and with the expansion mapping and having gaze information. This is the representation of that combination. And then you can project out into body space by unbinding, right? That will be extracting just one dimension, which is the body space information. You have to find out where that is. If you think through that, it's along the diagonals approximately, where the same spatial location arises given that combination. So if you shift this to the right, for the same gaze angle, this goes to the right. If you shift the gaze angle up, then it shifts to the right and so on. Think through that. So this binding through space, in other words, here in this logic, or let's say this logic, is really using the coordinate transform critically. And that's when the actual attentional bottleneck is the fact that we have these separate fields, and that we need to do the coordinate transform, which makes it impossible to do this on the whole scene. So rather, we cannot actually just write this direct input into working memory because of that coordinate transform. Good. So binding through space is just a special case of the more general idea that you're binding through a shared dimension. And I want to illustrate one other important dimension that we're postulating people are sensitive to, and that's sometimes not called in the working memory literature time. There's some ambiguity about whether it's event time or some kind of internal processing time. We're just actually working on that right now. In our account, it's actually something closer to what is called an ordinal dimension. That is, you have some inner state representing where you are in a sequence of steps. So first step, second step, third step. And Julia's original work proposed actually an architecture that autonomously generates a representation of that by making these transitions triggered by same events that you could, it could be perceptual events or could be attentional shifts or eye movements that create these events. And that's how you would have a like an ordinal axis. It's of course discretely sampled, but you're representing essentially that this is the second item, this is the third item that you looked at. And then this empirical work actually shows that you can, there's good evidence that what you link different features through the fact that they are returned to something that you observed at a certain time or in a certain serial order as you scan the visual array. And that is actually how we go to higher cognition. So when we think about concepts, we embed them in a shared dimension. We call ordinal dimension. We call it index here. The name is not so ideal. It would be the ordinal dimension. So for objects, this would be the first object you attended to, the second, the third, and the fourth, and so on. And for instance, here's the example where we would have object concepts, ball, tree, house, and we would have property concepts like big, red, and so on. And all of these concepts have a hidden dimension, that's this ordinal dimension, discretely sampled. And by being aligned along this, we would have, again, this ridge-like connection, cylinder-like connection, excited connection. We would then be able to represent that it's the ball that is red and the tree that is big and so on. That's how we get to do grounded higher cognition. So I can't explain the details of that, but I'm just hinting at that. So for instance, here you have nested phrases, the tree to the right of the tree that is below the lake and above the house, right? This is already the famous problem of two, in that there are two trees here, and these are two different instances of the category of trees, and you have to be able to keep track of that. And we'll do that by giving them different ordinal indices, because you're attending to the trees either in hearing the sentence or in then actually generating the sentence from looking at the scene. Do that separately in different moments in time. And actually the same is true about the relationships. We have the right off is the first relationship we're looking at, and below the second, and the above the third. So this will be like the symbolic graph representation of nested phrases like this. But that's not actually how we do it in the theory, and I'll show you that in a moment. Just to make this concrete, so we will be using this example in the simulations, and you'll see that we're talking about this tree here, right? That's the one that's to the right of the tree, that is above the house and is below the lake, right? So it'll be for you to orient. So we're using this object representation with binding through index, as I just hinted. So the phrase is encoded in working memory in these fields. So the tree is the number 2, it's a big tree, and so on. When you're then actually working on that is, for instance, perceptually grounding that, you need to extract again the concrete concepts, right? You now need to extract that, we call that readout here, that you're talking about a big tree, because you're currently focusing on the second object that you attended to originally. And similarly for the relations. So the relations here, left, right, above, and below are the relations here, and also verbs, which I'm skipping over, action words. And so there's a relation index. So the first relation that was attended was to the left, and the second was right, and so on. And now the critical thing, binding in this high cognition means that you're binding the relation to its arguments. Its arguments are target and reference object, right? So you have to say which object is to the right of which other object. And that is done by having a field that associates the relation index with the object index. And this is for a particular role. This would be what is role filler binding otherwise. So the role of target is, it's object number 2. That's the target of relation number 1. And there's a similar field for the role of reference object. So here the object number, for the relation number 1, the object number 3 is the relation object, right? And what that is stored up here. And again, when you actually want to perceptually ground that, you have to read it out and so on. There's more to explain. So this is the architecture that does that. I'm just hinting at the interface with the thing I just showed you. And to perceptually ground, that is to attend in the visual array to the object that is designated by these complicated nested phrases. You have this complicated architecture, which is actually always the same across all our different models. So it's only initially very complex. There are different feature space fields. There's a perceptual layer for that. There's feature extraction from the sensor surface. There's the relational logic, which I can explain, which involves coordinate transforms, where you have a relational concept. This is the synaptic pattern for it, and you need to be able to put it to any location in the space. There's actually even an index map that will store where which object lies in terms of the index, and there's some process organization. So here is a simulation of just the main concepts are shown. So we're grounding this phrase. This is here where this nested phrase is encoded. So these are the object concepts, and this here is the relation concept. So the relations themselves are encoded. Where is it actually? Left, right, actually not, maybe here, I don't see that. And then these are the arguments of these phrases. So let's run that, and you'll want to pay attention to the spatial attention field. So you're currently working here at this on the house. So that's the bottom. You're starting the street in a sense from the bottom up, and you put in the mental map. I put just the number here for the viewer. It's of course really just a layer in the 3D index over space map. So then it attended to the third object, which was this one, and now it tends here, I guess. I don't know what it tends to right now. And this is all autonomously organized. Oh yeah, it's got the one of those trees, and then ultimately would put, I think, something here in the mental map that's attending you to this tree, which is actually the target tree we're looking at. So this is the answer. This is what the tree that you want to look at, and it's attending to that tree. So the fact that it can be spatially attending to the correct tree shows that it can perceptually ground that relationship, right? Of course, understanding this in detail takes a bit more effort. Last example, you can do the same for action, right? This was perceptual grounding. This is embodied, so action. Like you have this complicated phrase, transport the blue donut onto a green plate, then transport the blue donut to the blue plate, and blah, blah, blah. All this is sort of represented here in a classical syntax diagram of such action. There's a subtle difference between action and perceptual grounding, but I'm glossing over that, not explaining that in any detail. So here, this is a similar representation of that conceptual structure where action verbs, linked to the arguments again through binding through indices, has the same kind of perceptual system that gets input from the visual array. It actually has this static system. It does active gaze shifts and has a little motor system that I'm also not explaining in detail. Here's the simulation of that. You always see the currently selective action here on top. This is this array. So currently it's trying to transport the yellow banana. So first it has to grab the yellow banana and then transport it to be on top of the red plate. When it's the grasping is really just symbolic that somehow this robot arm can connect to that when it triggers the grasp action. It moves it out of the visual array, so it's like not moving directly, but moving it out and then moving it back. So let's run that. So it focuses here on the banana and then puts it here off. Now it looks for the red plate, I believe, which has selected here, and now it will be moving it there and putting it down, and then it's done with that. And then actually the next phrase is coming up, transport the yellow banana on top of the blue plate. And so has already selected the blue plate here. And then the next phrase comes up, grab the green mug. And again, the green mug is attended. And so there's gaze shifts, this is the foveal field. This would be the parafoveal field. And you see these binding operations, there's some fluctuations here. That's why. So looking at it, all the sequence generation is generated autonomously by these instabilities triggering one after the other, right? So that's sort of a demo of how higher cognition, if I call that, this higher embodied cognition, right? Acting out sequences of action, how that can be achieved. So in summary, DFT is a special case of connectionism that has these two concepts of space and the instabilities of attractor states that lead to autonomy and binding. And and the goal of it is to provide a process account of grounded, embodied, and higher cognition. And of course, the claim in this perspective is that all higher cognition has this property. So even if you do mental arithmetic, our claim is it's not really fundamentally different from planning actions. That will be one of the things to discuss. So that closes my survey talk. I hope that we can organize a discussion. This video is only in emergency backup if I cannot be physically or not really be live. And I flash a few questions that one could discuss, and then we will come back to these slides and can really go through some of the assumptions. Why dynamics? Why attractors? Why is that right? Well, aren't all neurons responding transiently? Why populations? Why continuous spaces? What about the dimensionality of these fields? What about the localist assumption that's implicit in here? And then maybe contrast DFT to computational neuroscience. Is it computation? What about computational theories? How do they relate? What about DFT architectures? Are they just like cognitive architectures? VSA, for those who know, and NAF would be something we can make a contrast to. Well, I'll close this video and hope that the discussion can be organized in some way. Thank you.